I wish you all very happy Holi, and on this occasion of International Women's Day. I'm here to present a topic called non-destructive testing and evaluation of concrete structures. Basically, I planned this session not to introduce what is NDT or what is the implications of NDT, but instead, I'm going to talk about uncertainty perspective. In fact, non-destructive itself is bound to a lot of uncertainty and randomness. Further ado, let's get started. So this is the outline of the presentation. First, we'll introduce what is NDT, probably different methods in non-destructive testing for concrete structures. And then we'll talk about the significance and implications of the NDT, and we'll focus on the statistical methods and, very importantly, the uncertainty analysis. And that will be the major portion of my presentation. And then we'll discuss about what will be the further action from this point onwards, or what. So first, let me introduce non-destructive testing. I hope many of you in the audience will know what is non-destructive testing and different methods exhibited to understand the parameters of these structures. But then let me give you a quick overview. Then we'll get into the actual examples and case studies, and probably the numerical or the quantification of the the experimental results and so on. And basically, I will be presenting on the concrete structure, which is the reinforced concrete structure. So before we get into the actual NDT techniques, let's define what is NDT. And this is a famous definition. It's from ASTM, American Society for Testing and Materials. It talks about any methods or any testing procedure that does not causes damages or altering the physical and chemical properties of the structure. They probably would call it non-destructive testing. Like, this is like non-violence. We don't do any stuff, any harm to anybody. That's as simple as that, and we are not doing any damage to the structure. But then our objective is to understand the properties or the intricacies of our research or the experimentation. So that is basically the non-destructive testing. And to classify NDT, actually NDT is used in almost any field, from aerospace, structural engineering, and so on. The classification may not be common for all streams, but then I've classified NDT for concrete structures into 5. First, we talked about volumetric examination method. People talked about buckling and other related stuffs, and probably they want to study how it gets the buckle or volumetric transformation. In that case, people can try to use the volumetric examination method. And surface examination, in fact, most of our ultrasonic pulse velocity method, and in fact, to be more particular, our rebound hammer is exactly the surface examination method, when which it's acted on the surface of a member or the component. Then we'll understand that. Then it talks about integrity examination in terms of pin jointed frames and the other related mechanisms, where we'll try to understand the overall integrity. So that's basically an integrity examination. Then conditional monitoring. This is probably the recent terminologies. People use IoT devices to understand the concrete the parameters, like it. People even do a creep modeling using IoT devices and so on. So to understand how exactly that behaves, not necessarily that has to be a correlation, but then you need to have a substantial evidence and a frequent interval of times to understand how the structure behaves and something like that. And special NDT, like the unmanned vehicles and unmanned drones, are used to understand the offshore structures where the human access or the frequent access may not be possible. So in that case, it's probably the special NDT methods and so on. But there are umpty numbers of non-destructive techniques evolved. And in fact, most of them are hybrid in nature. Not a single techniques works better. So we will have a combination of techniques. So that will lead to a topic or the discussion called the non-destructive testing methods. The first and foremost is the visual inspection. Then we talked about rebound hammer. In this particular We will be studying the uncertainty analysis pertaining to the experiment results of the rebound hammer. And then we'll talk about ultrasonic. In time permits, we'll also talk about the electrical resistive method and so on. And then we'll talk about, I know this are the things that will be planned for this. And then there are other methods like pulse echo method, Windsor probe test, acoustic emission tests, and radar tests, and so many techniques like carbonation tests and radiography, and so many things like, and some of them are even an equipment that can be, per se considered as an method. Say, for example, LVDT is to find the deflection. Probably they can use it to understand the structure without damaging the structure. And talk about inclinometer, tilt meter, and transducers, and so on. And the polarization resistance technique, galvanostatic method, and so many methods are there. In fact, 30 plus methods are available, but I've quoted few of them for, to give a clear understanding of different NDT methods available for concrete structures, basically. We call Smith rebound hammer itself till now. And then it comes in a different varieties also nowadays. It comes in a digital portable device kind of arrangements and so on. But it's still be one of the important non-destructive testing or quicker access of a quicker estimate of the compressive strength. It may not give you more accurate value, but then it will give you quite a good picture of about the structure or something like that, or existing structure or something like that. And it basically does by hitting on the surface, and by the velocity of the rebound, it will give it will return a number called rebound number, and based on that we will use a graph to understand the compressive strength and so on, right? And it's the rebound number, and some they refer to the rebound index also. So this is a typical component. Like this one, component one is very important, called impact plunger. And then there is 21, which is lock nut, that locks, then releases. And when the releasing process, we probably gets the rebound number and something. And this is from Humboldt. It's one of the good manufacturer of Smith rebound hammers. And let's take an example. I'll just all right, so yeah, here we are. This is the structure probably which we considered for the analogy. We take a wall structure, 1000 mm, which is 1 meter by 2 meter and 150 mm thick, and probably we'll see, we'll study the effects of non-destructive testing, or probably we'll use the Smith rebound hammer to understand the implications. Right? So this structure of 1 meter by 2 meter, 150 mm thick, and this is the planar surface. It's a wall structure, and then we'll divide them into grids of equal spacings, like say 250 mm. So we have divided them into equal spacings, 250 mm, and then which has got its the peripheral axis, the grids, and then the intersection of the grids is the point when which we'll understand the compressive strength of this whole structure, right? So for this example, we have got 32 grid points. If there are more number of grid points, the experimental results we will get will be approximately more effective, because more the closer, so it's just like finding out the compressive strength at all the places, and the average will yield a approximate result. But then for this example, I've given 32, each is the distance of 250 mm and so on. All right, so it's a wall, so we'll be taking a look at the horizontal implications of the rebound hammer. And this is the chart I'm talking about, by which we will be finding out the compressive strength, and you can even find out cube and cylinders corresponding values also. If we get a rebound number of 30, and then our is B, which is a wall kind of inclination, and then B has two things. One is a continuous line, talks about cylinders, whereas the dashed line, it talks about cubes. So 30, when it intersects cube, that can be something around 22, 23 probably. So that is the implications of the rebound number 30. And this is in PSI, pound per square inch, and this is in MPa, Newton per millimeter square. And this is how we will find out indirect, determination of compressive strength with the rebound number. And this is what the general implications. If the rebound number is greater than 40, we consider it to be a very hard layer. And 30 to 40 is just hard, and 20 to 30 is fair. And anything less than 20 is not advisable or very poor layer. And the 0, which is called delaminated, sometimes when you have too much of mortar in an area, and not even having the fine aggregates, it's just like cement piles, then probably when you use NDT, it can break, and then it can yield probably less than 20 and lesser than 10 also. In that case, we can probably don't consider that as a delaminated, but instead repeated trials in the nearest locations can also yield sufficient resistance, because the overall values we take it as an average. So if you have a lesser value, the law of averages plays a huge role. So I'll explain you that. So this is the test results, probably sample test results for the grid number 1 to 32. For grid number 1 to 32, we have the test results. For grid 1 is 30 Newton per millimeter square from the rebound value, the compressive strength, and we take cube compressive strength. And then I can also take cylinder compressive strength. For this example, I've taken cube compressive strength. And then when you add all and divided by 32, when you take the average mean value, it is 36.28. And remember that this is for M30 grade concrete. For M30 grade concrete. And for M30, and if you have an average of 36.28, it's probably one of the good things that you can appreciate. Your concrete is really good enough to withstand. But this is just a single trial. You have to take multiple trials to understand the true compressive strength value, or the actual, or something that is closer to an actual, something like that, right? So, but by seeing this, we might think that it's okay. But when we do a statistical analysis on this, then we probably understand, the implications of this experimentation, right? So this is a very important part. So far, we talked about only NDT and experimental results. And from this point onwards, we'll be looking into the statistical analysis perspective. And then we'll build up the idea of statistical analysis for the uncertainty analysis. And this method, we will be using the basic statistics like mean, standard deviation, and coefficient of variation. First, we need to have an underlying assumptions. The two assumptions are very important. One is we consider compressive strength of specimen as random variable. In case you have studied probability and random variable, you probably understand the implications of random variables, why we designate compressive strength as random variable. We cannot have it stochastic or any other variable, but random variable fits is more perfect. And compressive strength, it is normally distributed. Like if you do a compressive strength test, not necessarily, the NDT method, but general compressive strength test itself, probably when you make numbers of concrete cubes and get cured, and for 28 days you test it, you will not get same compressive strength value for all the samples, even though all the samples were manufactured using the same degree of workmanship and the same materials. But you see there's a variability. But if you put them in a graph, and if you try to find out the distribution, it will always be Gaussian distribution. So the bell curve, you will probably see the normal. We'll talk about that a little later. So that is basically an underlying assumption. And for this, any test, you need to perform as per the governing standards. We use BIS standards for our testing. And this is the basic arithmetic mean. We talk about the different samples, the compressive strength values divided by the total number of samples. And a very important thing I want to specify here is this is the sample standard deviation. Remember, it's not divided by n, it is divided by n minus n. The reason is that we are not taking it values at all the point. We are taking only the sample points of the entire region. So which means that these things are representative samples of the larger volume of concrete, right? So that is why it is a sample standard deviation rather than population standard deviation. But population standard deviation will be divided by n, but sample is n minus divided by n minus 1. And then we'll talk about coefficient of variation, which is the fraction of standard deviation to the mean, but it always represent in terms of percentages. So we'll multiply it by 100. And this is a very important thing. So far we talked about sample standard deviation, mean, and coefficient of variation. This is probably a very interesting thing that you should really take a look at it. It's called reliability of the compressive strength. Normally, when the experiment is over, people does statistical analysis, but they stop with that. There is something that beyond an experimentation values or beyond a statistical analysis is the reliability, when it will give you actually the test method itself is effective, or the probability of success of the experimentation. So that is also a very important factor that everybody should understand. I have removed few derivations, but this is the final derivation, which is the probability of failure. The ranges from -∞ plus characteristic compressive strength, and this is the design compressive strength, and with the difference of which is the characteristics of the strength. When you do an integral, probably you'll get f of x into dx, and this will become mean compressive strength. So this is one of the important things. I have ignored all the derivations. You can probably take a look at that, the relationship between service life and the probability of failure and something like that. So that's a very big derivations. Probably you can take a look at that. And even this integrals, we can further reduce it into a formula kind of thing, because we use normal distribution for our assumption. Like, so we assume that the compressive strength will be like in the normal distribution. So the probability of failure gets converged into, this is the normal distribution function of characteristics compressive strength minus mean compressive strength divided by the standard deviation. This is sample standard deviation. So we'll be finding out the probability of failure of the experiment which we have carried out, and then we'll see whether the experimentation is good or if the reliability of the experimentation is satisfactory. And that's the basic understanding. The first few percentage of our uncertainty analysis is understanding the reliability. Uncertainty and reliability is almost the inversely proportional. More the uncertain, less the reliable thing, and lesser the uncertain, more the reliability, and something like that. Right. So finally, probability of failure, we'll have this under the normal distribution curve, and then we'll have a probability of success, which is called reliability, which is 1 minus probability of failure. Total probability is 1. 1 minus probability of failure will give us a success, or 1 minus probability of success gives probability of failure, or something like that. So I'll illustrate this concept then normal distribution graph. So this is what I've explained you with this characteristic compressive strength, mean compressive strength, and mean compressive strength from the experimental results, and characteristic compressive strength is what we generally do. It's a design compressive strength. For M30, it is 30 Newton per millimeter square, M35, it is 35 Newton per millimeter square, and M40, it is 40 Newton per millimeter square, and so on, right? So that's a design compressive strength. Right. This is the total probability. Probability of 1. This is the normal distribution, and minus 3 sigma to 3 sigma. And I think if you are a teacher, probably you know this when you do this for a relative grading, like the percentage of your class, and then the percentage of failure in your subject or something like that. But this is applicable to the compressive strength test also. We can bifurcate them into two: probability of success, what called reliability, and other than that, we call it a probability of failure. So this particular curve, left side curve, will determine the reliability of our test. If this particular probability of failure keep on increasing it, say for example, if it gets increased here, then that's a total disaster. Then even though you have a good fruitful results, your compressive strength is pretty good, that's not going to be acceptable. So because your experiment itself is not in the range of accepted limits, and so on, right? So generally it doesn't happen. Generally, it happens like minus 2 sigma can go to minus 1 sigma and so on. Like it will be something around 30%, 40% failures, but anything beyond 40% failure is totally not acceptable. Right, so this is the discrete frequency distribution. In fact, we'll talk about continuous frequency distribution a little later, but discrete being, simple data like 32 samples, we can probably count them using arithmetic mean or something like that, right? So this is the arithmetic mean, and we'll take all the samples and we'll add together, and then we divide it by 32. 32 is the total number of samples. Number of samples, and the mean compressive strength is 36.28. Probably you can take them 37 for ease of computation. You can take 37. Once you find out a mean, next step will be finding out the sample standard deviation. Right. The sample standard deviation. Actually, nowadays you can find them in calculators or even Excel sheets. But then I'll do the old-fashioned stuff like taking the compressive strength value, finding the deviation. Mean is 37, x bar is 37, minus 30 is 7. See, 37 minus 41 is minus 4, and so on. And you have to find out the square of the deviation. And once you find out the square of deviation, you need to calculate the sum of the square of the deviation, which is 629. 629 divided by n minus 1, and you have to take the whole root of it. That will become the sample standard deviation. So 629, which is the sum of all the square of standard deviation, divided by 32 minus 1. It is not 32. It's not population standard deviation. It's a sample standard deviation. When you take 32 minus 1, it will be 31. And if you take a square root of that, like root of 20.290, it will be around 4.5 standard deviation. So our results, which means that each value gets differed by one another in the terms of 4.5 Newton per millimeter square. So that's the the implication of standard deviation. The reason we talk about this is that when the standard deviation is less and the mean is high, when the standard deviation is less and the mean is high, we'll have a lesser value, lesser coefficient of significance. But if you have more standard deviation and mean is approximately in the same level, probably you'll get the more coefficient of variation. So I'll explain you that. So coefficient of variation is nothing but standard deviation divided by mean. We will generally express them in terms of percentages. So it is 4.5 divided by 37 into 100, which is approximately 13%. So which means that this is part one of the uncertainty analysis, in which we say that 13% is what gets deviated. So I can probably say that 87% of my analogy or my experimentation is perfectly valid or perfectly good, or as equivalent to a true, but it just differs by 13%. But if I can make it lesser than 13, less than 10, less than 8, then the amount of certainty of your experimentation will be pretty high. So this is an important inference that you should know on the coefficient of variation and its implications in the experimental results. This is part one. Then we talk about using these values, we'll be finding out the reliability of the test results. Right. So as I told you, reliability is characteristics compressive strength minus mean compressive strength divided by sigma, which is the sample standard deviation. And this is a characteristic compressive strength for M30. It is 30 Newton per millimeter square. And the mean, which is X bar, probably can see that we got X bar as 37. So I have put X bar as 37 divided by 4.5. And then when you do a computation, it will be minus 1.555 and so on. And you stick to two significant figures, because in normal distribution graph or tables, we'll probably have to only find out 2 decimal places. And this is the probability of failure. We say that our probability of failure is approximately equals to the normal distribution function of minus 1.55. Here, the minus and plus has got huge implications. Kindly make a note that if it is plus, the entire meaning will be different, right? Something like that. So we say that our mean is greater than the characteristics compressive strength. So that's why it will be in the range of negative. When the normal distribution values in terms of negative, so our experimentation has got positive contributions, which means it's more reliable. If it is positive, then we are like 50% surpassing the reliability value or something like that. So I'll explain that. So probability of failure, which is equals to the function of, normal distribution function of minus 1.55. You can take a look at this particular normal. This is the normal distribution table, Z table. Probably you can see that in statistical textbooks. Our value is minus 1.55. So I'll take minus 1.5 and I'll go to 0, 0, 0.1, 2, 3, 4, and 5. When you add, probably you'll get minus 1.55. Just put the significant figure of here, you'll get minus 1.55. And then that corresponding value, I can zoom it bigger so that you can understand this. This is minus 1.5. And probably you can take a look at this, 0.05. And then you get something around a value called 0.0606. You might wonder what is this value, but this is the probability of failure. Remember, this is the probability of failure. Let me go to this. Probability of failure. So once I found probability of failure, 1 minus probability of failure will be the reliability. So 1 minus probability of failure value from the Z distribution will give us 0.9394, which is in terms of percentage, it is 93.94, which means that my experimentation is 94% reliable. So which means that nobody can make 100% reliable, but 99, 98 probably can be more reliable. That is why in an advertisement, say the disinfectant advertisements, probably the company that sells disinfectant liquids, they'll say it kills 99.99% germs. They don't say 100%. Nobody can ever get 100%, but more closer to 100% is considered to be more reliable, right? Something like that. So that's how we understand, right? So not only the compressive strength is higher, and with that we'll conclude that it is more reliable, but the experimentation itself is more reliable since it has got 94% of reliability. So this is like 15% of what we talk about the uncertainty analysis. The actual uncertainty analysis starts right now. We have 20 minutes time, so we'll quickly run through what is the reliability. We have talked about reliability, we talked about what is uncertainty and different types of uncertainty, and probably many of your researchers, it is mandatory to include the uncertainty analysis in your computation. That's what peer-reviewed experts, peer-reviewed journals, the experts, and even for thesis, people need to understand that in detail. Let's get into the uncertainty analysis. So why uncertainty analysis, the question, right? So in scientific research and experimentation, there are two things. One is called repeatability and reproducibility. What you could do it in your laboratory for a particular sample, for a particular day, for the particular equipment, that is it repeatable even after 5 years. So that is basically what we call a repeatability. And what is reproducibility is, if you present a research article, even though if I able to get the same materials and kind of a similar equipments, but not certainly in your condition, laboratory condition, in my laboratory condition, will I be able to get approximately that with some losses due to the change in factors, not necessarily factors, environment? Will that be an effective strategy? And that is what we call a reproducibility. So any experimentation or research, generally the experts look into repeatability or reproducibility. So this is an important terminology that everybody should understand. So when you do an experimental based research and something like that, and that will be leading to a topic called uncertainty analysis. But actually, repeatability and reproducibility can be effectuated, but with some constraints, and that is what we call uncertainty modeling and something like that. But there are a lot of things that we can talk about uncertainty. Due to the lack of time, we'll quickly run through 3 types of uncertainty: type A, type B, and combined uncertainty. And then you can always use this for any of the testing methods or experimentation, not necessarily non-destructive or not necessarily rebound hammer. You can even take a look at that in electrical resistivity, where you draw corrosion contour, in which you can probably try to incorporate uncertainty analysis also. The first is the type A uncertainty. And remember that type A talks about measurement uncertainty, And type B is also measurement uncertainty, but not necessarily the experimental result. But type A talks about measurement uncertainty for the experimentation. It can be classified as the statistical uncertainty. Whatever we have discussed earlier, the discrete frequency, all these things plays a huge role in the experimentation. Like as I told you, reliability can be a key takeaway from you, from me, for you today. The other factors like non-experimentation or other things also matters in terms of uncertainty. So first we'll talk about type A, which talks about the experimentation uncertainty. And it's also known as statistical uncertainty because we'll be looking into the statistical parameters like sigma and then the mean and so on, right? And it is basically an systematic error that you will encounter when you do the experiments, something like that. For example, if you do a repeated experiments, say compressive strength test, as I told you, could be a good example. Even though the same sample, same materials, when you test it again, you may not get the same compressive strength, right? Something like that. So same materials, same workmanship, but why we are not getting it? So that's what basically the uncertainty, and that is what type A uncertainty is all about, right? And the formula is U of A, which is uncertainty type A, which is equals to sigma. This is also sample standard deviation divided by root of n. N is the number of the samples. And say, for example, a rebound hammer experiments, grid number 9. Let me show you that quickly, and then we'll come back to this. Grid number 9. Say this is grid number 9. And what is the value for that? Initially, the grid number 9 is 42. Right. So that is 42. Right. And then we'll try 4 more trials. Like when I use rebound hammer, I didn't get 42 Newton per millimeter square, but instead I get 40, 39, 41, and 40. So there is an, even though I have repeated, but that value, none of the values are correlate to this. But sometimes there could be a value that correlates to this. But then like in this case, none of them correlates the previously given value, right? So if I stop with the first trial, you see 42 is the highest among the all. If you take this experimental value results, 42 is the highest, I guess. Yeah, 43 is there. 42 is the second highest. So probably when I tried again, but it doesn't yield 42. In the first instance, I got 42. With that, I cannot really conclude that this particular region, that particular slot grid is having a high compressive strength, something like that, right? So that will, in fact, change the average. If I take this inclusive in average and this inclusive in that average, and see the entire average values get varied, and that's how we are lacking the true compressive strength, right? So what we can do is type A uncertainty talks about the sigma divided by root n. This is sample standard deviation. To understand sample standard deviation, we need mean. First we'll calculate the mean, which is x bar, then x bar minus xi, which is x bar, which is 40.4 minus 42, 40.4 minus 40, and so on, square of the deviation divided by 5 minus 1. So I've got 5 samples, 5 minus 1. Generally, there's a rule, or we can take a look at that. Trials that has to be repeated as 5 to understand the type A uncertainty, but it's not necessary. You can even try beyond, or it could go with 4 or something like that. But don't have a lesser sample and try uncertainty analysis. That's lesser trials. I beg your pardon, not samples, lesser trials for the uncertainty. The more you try, the more clear picture it will give you, something like that. And then it will give you a standard deviation of 1.30. You can see this is one grid only. One grid itself, it gets varied by 1.3 Newton per millimeter square, right? So think of our uncertainty of 4.5. So that can be altered also if you take multiple trials, something like that, right? Then we talk about type A uncertainty. This is equals to sigma divided by root n, which is 1.30, which is sample standard deviation, divided by root of 5. Here it is not n minus 1, just 5. and you'll get something around 0.58. Approximately, you can equate to 0.58 Newton per millimeter square. So what does this uncertainty means? So this uncertainty probably, if you have taken Walter Levin's classical mechanics, MIT courseware, probably Professor Walter Levin will tell you all his readings with has got its uncertainty value. Like he calls them as, or the physicist calls them as an errors in their measurements, something like that. So all his calculations, even the first video, this is the first video actually, in his lecture, the classical mechanics, it talks about uncertainty. Without uncertainty, many, the scholars may not accept the values, something like that. So the 0.58, this one, right? So which means that this is our trial 0, which is our initial experimentation, and we have done 4 trials, extra trials, and that plus or minus 0.58. So which means that my value is not 42, it could be 42.58, or it could be 42 minus 0.58. What is 42 minus 0.58? It's something around 41.42. 42, right? Something like that. So that's how it is, and so on, right? So this is a typical thing. And the degree of freedom, right? So this is not a degree of freedom in structural analysis, but in terms of uncertainty, for type A uncertainty, the degree of freedom is n minus 1, which is number of samples minus 1 is equals to 4. Degree of freedom itself is a very big concept, so we'll be probably skipping that for this particular thing. Maybe for an uncertainty analysis of the other lectures, other experiments, we can probably talk about that. Right. So that is type A. Type B, we talks about non-statistical uncertainties, and type A is only one. It's experimental error. But type B, it could be anything. It could be due to the temperature, or it could be any factor that is affecting our experimentation. Not necessarily the test methods or the procedures, but anything like even the instruments. If you have not done experimentation in a very calibrated or very sound instrument, then that's an error. Right, so that does not gives you a clear picture. Or if your microstructure were taken in an equipment which is, scanning electron microscope, and that is not calibrated for so many years, that could be an erroneous, but not guaranteed that will be error, but it could be misleading or something like that. The resolution can go off, something like that. So that's kind of a pretty much the instrumentation error. And resolution error also. How zoom you take a look at that. So that also matters most in terms of the uncertainty. And the formula is very simple. UBI, which is UI, which is the randomness in terms of the experimentation. So we'll talk about that a little later. For this example, we have taken Gaussian distribution. This is a confidence interval. How confident are you when the analyzing it? Like generally we take 95.45 confidence interval, and we'll have a factor called a by 2. So I'll tell you what is a by 2. A is the uncertainty associated with the equipment at 95.45% confidence interval. And the degree of freedom of any distribution, probably normal distribution, is infinity. So it does not plays a huge role in the type B uncertainties. Right, so this is a typical example. The same rebound hammer example. We don't have a calibrated equipment. In terms of normal distribution function, and then at 95.54 confidential interval, and we get something around 0.4 Newton per millimeter square, right? Something like that. So the uncertainty from the manufacturer certificates, we somehow got it, and it has got different thing. Like this is what you get it from a calibrated. When you buy it from a good company, they'll give you a certificate called calibration certificate, when which you'll get this uncertainty and K values and confidence interval. So this is a two-part. One is we are calibrating at the laboratory, and the manufacturer's calibration, and all those things can be lead to uncertainty. Probably the new equipment, if you buy new equipment and if you try calibrating it, it will be matching exactly with the manufacturer standard. But as the year progresses, wear and tear can happen, depreciation, excessive use can put down the certainty of that equipment. So the manufacturers and your calibration might have a differential value. So say for this example, for me, when I test, the uncertainty comes around 0.4. In this example, I got 0.58. Say, for example, I'm getting at 0.4 for 95.45 confidence interval at the normal distribution. And for the normal distribution, we'll get the value of A by 2, which is A is equals to 0.4. So the type 2 uncertainty or type B uncertainty will give something around 0.4 divided by 2, it is 0.2. So which means that not only the experimental value or experimentation uncertainty, I need to consider that the equipment itself is giving me an uncertainty of 0.2. When the equipment gives me 38.2 Newton per millimeter square, it is 38. So it is giving me 0.2 extra. So that should be noted down when you do a calibration or this testing and something. But let's take a look at the manufacturer's thing. Manufacturer is very simple because they will give you expanded uncertainty. Expanded uncertainty is the range of value they test with the reference sample in the laboratory, and then they lie between certain range, and that range is what we call it 0.2 Newton per millimeter square. So the rebound hammer from the manufacturer gets me only 0.2, and the K value they specify. This K value we'll get it from the manufacturer certificate. If not, we need to assume it based on our experience or based on our tolerance value of so many factors, like the lab technicians or the lab instructor will tell you based on the particular make, particular equipment's usage for quite a long time and something like that. And it will give me only 0.1 Newton per millimeter. So which means that manufacturer itself say that it is can deviate by 0.1, but actual calibration can be 0.2 and so on. So which means that you can take either one of this. Generally, it is advisable to take the maximum. That is what Walter Levin also will say in this video. Whichever is maximum, because it's an error. Why do you compromise an error by taking it less error? It looks very fancy, but it's not true. So if you give me the true value, people can accept that. So if I want to take the error values of type B uncertainty, I just take 0.2 rather than 0.1 or manufacturer. Or owing to its usage, I may say that 0.1 is not possible anymore. It will be 0.2. There could be other uncertainties. This is generally for analog equipments. Nowadays, rebound hammers, you'll get it in digital, equipment. So the readings variability may not be that high because digital will give you bang values like 0.23, something like that. So that's kind of a pretty much an interesting. But for the analog, remember the classical UTM machines where they have a KGF. The people have hard time in converting that into MPAs, right? So that's kind of pretty much where you have to really worry about resolutions and something like that. And resolution, generally resolution by 2 and divided by that K value from the manufacturer. And rebound hammer, if you buy any rebound hammer, you'll have a manufacturer card and they will say 1 or 2 Newton per millimeter square. They does not guarantee you. If it is 38, it is not 38, it is 37.8. So, but I beg your pardon. It is not 38, it is 36. So 2 Newton per millimeter, it's not 0.2, it's 2 Newton per millimeter square. So the manufacturer themselves will say, for an analog, it can go plus or minus 2. So it can go the other side or the other side. So that is why we take an average of it. So 2 divided by 2 is 1. And divided by the K, we generally take it as 2. For this example, we have taken as 2 because it's given in the manufacturer thing. And that's how type B uncertainty is 0.5. Remember that resolution 0.5, and you can see this 0.5, we could have correlate this here. Yeah. So without uncertainty, this is the actual value that we will presume. But with uncertainty calculation, we have got something like this. You see, even this resolution, the equipment resolution is also 0.5. So which means that is almost true. Generally, if it is 42, it is 41.5. So that's how the equipment itself is. So this is particular, the resolution characteristics and something like that. And few more things. Combined uncertainty, which is nothing but combination of type A and type B. which is a factor called the root sum square, RSS, where it is a square of type A uncertainty and square of type 2 uncertainty, which is, it cannot put everything, but instead, whichever is valid. Say, for example, in this example, calibrated at laboratory or calibrated from the manufacturer, whichever is higher is what I recommend you to put. So, but not both, right? It's not 0.2 whole square plus 0.1 the whole square, not like that. So any one. So similarly, you have got n numbers of type B uncertainties, and remember that each of these are not are independent and uncorrelated. So if you take this and this, both of them talks about the same uncertainty and k value, but that is not what we're gonna do. We have to give independent uncertainty. Say for example, resolution, or in terms of temperature, humidity, probably whatever factor might be uncertainty due to that, all the things you can add them, and that will give us combined uncertainty. Combined uncertainty is actually the standard uncertainty. Even if you have an NABL laboratory, probably this is what they find out in a bigger Excel table of columns, when which the type A, type B put together, and this they consider the true or the final uncertainty. All right, so I think I've taken good time to explain you what is uncertainty mechanism. There are other uncertainty analysis or quality or qualitative metrics like the keywords control charts or cumulative sum. They probably call it Q sum charts or VMAS techniques and so on. So since want of time, so I'm stopping at this point. So thank you very much for listening. So I'll be glad to answer if you have any queries.